So this is the last and second video on evaluation of assurances and annuities in contingencies and actuarial mathematics, and I'm covering life annuities payable m-thly. So this is now trying to generalize these life annuities that so far we've been dealing with only paying yearly or continuously, but now we also want to look at the cases where these annuities might be paying every month or every day or every week or some other time interval other than a year. Okay, so the way to understand this is per year there will still be a unit payment. We're still assuming that there's a unit payment per year. And so in previous videos, when I talked about annuities that are payable in advance or in arrears or continuously, there was always one payment in that year, and that payment was of size 1. And to get any other sized payment, we had to multiply that annuity factor by a greater amount. So if the annuity payment was 100,000, I would take 100,000 times by my expected present value factor for the annuity. Okay, then now what I'm dealing with is annuities that are payable m-thly. So within a year, what I'm saying is that there's still going to be unit payments. So this means that if I'm having m payments in a year, then each payment must be of size 1 over m. And the reason for this is so that my payments for that year still sum up to 1. So I have m payments of size 1 over m in one given year, and so 1 over m plus 1 over m times, that's m times by 1 over m, just equals 1. And these payments are occurring at regular intervals every 1 over m units of time. So previously I had a year as my unit of time, but now I'm dealing with m periods in that year, and so this is payable every 1 over m years. So the first payment could be either at 0 or 1 over m, but then subsequent payments must happen every 1 over m years. Okay, now discounting is obviously different because I can't discount by an entire year for each of these payments. This first payment that's happening at time 1 over m needs to be discounted by 1 over m. Likewise, the payment that's happening at time n minus 1 over m, the payment right before the end of a term, must be discounted by n minus 1 over m years. Okay, where v here is the yearly discount factor. So 1 plus I to the negative 1, where I is my yearly effective rate of interest. And then I must also have different probabilities here. So now, in order for this payment to be received at time 1 over m, the person has to survive from time 0 to time 1 over m. So now I have the probability that a life aged X survives the next 1 over m years. This would be the probability that a life aged X survives the next 2 over m years, and etc., etc. So what essentially is happening here is I'm dealing with these people surviving for parts of a year, and this requires an assumption to be made about the mortality within that year. So we could make uniform distribution of death assumptions, we could make constant force of mortality assumptions, we could make Balducci assumptions. Okay, now let's move on to some formulae that are useful for this. So there's two ways to go about understanding these or writing these annuities payable m-thly, these life annuities payable m-thly, in terms of summations, and I'm going to show you both ways. So one of them I'll do for in arrears and one of them I'll do for in advance, just to avoid being repetitive. So the first way is for this annuity payable m-thly for a life aged X in arrears. So this is going to pay at time 1 over m, it'll pay at time 2 over m, 3 over m, etc., etc., for the rest of this person's life until they die. So if they die in their 60th month from now, then they won't receive that 61st payment, okay, at the end of that 61st month. Okay, So rather, if they die in the 60th month, they won't receive that 60th payment because this is an arrears. So the first month's payment happened at the end of the first month, 60th payment, end of the 60th month. Okay, so this equals to 1 over m, because each payment now is of unit 1 over m, is of a 1 over m. So initially 1 unit of payment per year, now it's 1 divided by m because it's m payments. Then sum to infinity from t equals to 1 of v to the t over m, lx plus t over m, all over lx. Okay, so the way that we should understand this is, first of all, discounting. I discount each of these payments by time by v to the 1 over m. This first payment by v to the 1 over m, second payment by v to the 2 over m, and so my t is my index that'll count up from 1, because this is an arrears, all the way until infinity. And each of these payments occurs with a certain probability, and that probability being this, lx plus t over m over lx, which essentially will be equal to t over m px. Okay, now the second way to understand these is as follows. So I have AXM, an annuity payable in advance, and an m-thly annuity, which will equal to 1 over m, once again for the same reason as above, sum from t equals 0 to m minus 1 of a whole life annuity payable yearly in advance, deferred by t over m. Now, if I'm summing this up from time 0 to time m minus 1, then I'm essentially having m payments, or I'm looking at m different annuities, m different whole life annuities. One of them will be a whole life annuity that starts immediately when t equals 0, and then that will pay at each yearly interval following that. So it'll pay at time 0, it'll pay at time 1, it'll pay at time 2, etc., etc. So if it looks like this, it'll pay at time 0, time 1, time 2, time 3, and so on. So that index t equals to 0 deals with all those payments. Now when t equals to 1, I'm dealing with all the annuities that are offset by 1 month or by 1 period of time, depending on what period of time I'm using. So then what I'm essentially saying is I'm adding a payment that happens at time 1 over m, a payment that happens at time 1 and 1 over m, payment that happens at time 2 and 1 over m, payment that happens at time 3 and 1 over m, etc., etc. And then I keep adding in all the rest of these lines until I have m in each year. And then I've covered essentially all the possible payments that could be occurring, okay, through m different whole life annuities. All right, now the next formula that we need to understand is AXTM, so a whole life annuity in advance deferred by t over m years, and this will approximately equal to AX minus t over m. Okay, so that's just an approximation for us. And then the next formula that's important is as follows, and this next formula has an extremely long proof that actually requires you to use the Taylor expansion of e to the x. And so I would bet a lot of money, now I'm not a betting man, but I would bet a lot of money that the proof would never come up. Maybe part of a proof, but really I think this proof would never ever come up. And so I'm not even going to waste my time talking about it, but it is something that you should probably know regardless, in case you are that unlucky person, because if it comes up, it could come up for a lot of marks. All right, so this is something that we're just going to have to know, and this is a extremely important formula. You have to use this formula an immense amount in your workings. You have to constantly convert your yearly annuities into m-thly annuities, and this formula is golden for that. You really need to know this formula. I can't stress enough. The reason why is because the tables that we get, the life tables that we get in exams, all deal with these yearly payable, these annuities that pay yearly, and sometimes we have to deal with monthly things, and so this formula always comes in handy. Now, another way to write this formula is, okay, not to write this exact formula, but a similar version to this formula is for the arrears payments, and it's no different except for I have a plus instead of a minus. Okay, now because the proof is so long, there's not really much of an intuitive way to think about this m minus 1 over 2m, but there is a way to help you remember whether you should subtract or whether you should add the payments for these approximations. Now, here, in any given year, I have a unit payment that's occurring, and that unit payment is happening at the start of the year. Okay, so no discounting in that particular year. Here, I'm still having a unit payment, except it's split up into m payments of size 1 over m. And so some of those payments will be discounted by time and probability. And so I'm expecting this m-thly annuity to be smaller than this whole life annuity. And so if this is going to be smaller, my approximation must have a subtraction of some positive constant. And I subtract this positive constant in order to get this smaller number. Okay, so that's the reasoning here. And if you apply that logic in the reverse way, you'll understand why you need to add here. The reason is because this unit payment is happening at the end of the year. This is a unit split up into m payments, and these payments happen regularly throughout the year. And so this has all of those little m pieces right at the end being discounted. This has some m pieces closer to the start of the year, and so discounted by less. And so this is going to be larger than this, which has its unit payment discounted by more in total than all the payments here are discounted. And so I must add m minus 1 over 2m to this in order to get my m-thly annuity in arrears. Okay, another thing that's very important is AX in advance for m payments is equal to 1 over m plus AX m. Now this is literally just the generalized formula of this. You'll see why that's true if you just substitute in 1 for m. Okay, so it's just the generalized formula of that. Then the last thing that's important is AXN. So this is a term annuity for n years that is payable m-thly. Okay, so don't think now that even though this is payable m-thly, and let's say m is 12, so this is payable monthly, don't think that this is the number of months. This is still the number of years. Okay, and this approximately equals to AXN minus m minus 1 over 2m into 1 minus VN NPX. Okay, so that's it for life annuities payable m-thly. Really, the most important formulae in this video are these two. This one is also extremely important, so memorize them off by heart. Make sure you know how to use them and practice a lot with them so that you never have to forget it or never have to make a mistake with these formulas. It's a mistake that you don't want to make. Now, okay, another thing I must quickly point out is for all of these m-thly annuities, the number that you must multiply it by in order to get the annuity present value that you're looking for. In this case, for these yearly annuities, you're multiplying by the payment size. Here, you are not actually multiplying by the payment size. You're multiplying by the payment size times by M. So if you're receiving, let's say, 1,000 Rand a month, so M is 12, then the coefficient of this should actually be 12,000. Okay, so that's all I want to say, and good luck for your studying.